When you start building mental models of secure systems, it is natural to focus on the code your team writes, because that feels like the part you can see and control. Modern software, however, is built from layers of third-party libraries, frameworks, containers, and services, and a surprising amount of your system's behavior comes from code you did not author. That reality creates supply chain risk, meaning security can fail because something you depend on is vulnerable, malicious, abandoned, or simply used in an unsafe way. The challenge for a security architect is not to eliminate dependencies, because that is rarely possible, but to control how dependencies enter the system and how their risk is managed over time. This is where source composition analysis becomes essential, because it turns a vague worry about third-party code into concrete visibility and policy decisions. By learning how to apply this discipline, you can reduce surprise, limit blast radius, and make dependency risk a managed part of architecture rather than an ongoing source of uncertainty. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Software composition analysis, SCA, is the practice of identifying, tracking, and evaluating the third-party components and dependencies that make up a software product. The first thing to understand is that SCA is not only about finding known vulnerabilities, even though that is the most famous use. It is also about knowing what you actually ship, which is harder than it sounds when dependencies are pulled transitively through other libraries. It includes understanding versions, licenses, update status, and the relationships between components, because those details affect both security and maintainability. For a beginner, it can help to think of SCA as an inventory and health check for the code you inherit, whether you asked for it directly or it arrived indirectly. Without an inventory, you cannot make rational decisions about risk, because you do not know what is present. With an inventory, you can ask better questions about exposure, impact, and mitigation options. Supply chain risk in software has several common shapes, and SCA helps because it makes those shapes visible early. One shape is a vulnerability in a dependency that becomes exploitable in your environment because the vulnerable function is exposed through your interfaces. Another shape is an update that introduces breaking changes or insecure defaults, causing behavior drift that weakens controls. A third shape is dependency confusion or package substitution, where attackers try to trick build systems into pulling malicious packages instead of intended ones. There is also the risk of abandoned dependencies, where maintainers stop shipping fixes and the component quietly becomes a long-term liability. Finally, there is the risk of overprivileged or overused dependencies, where a library is granted access to sensitive data or privileged functions far beyond what it needs. These are not exotic risks for advanced organizations only. They appear wherever software is assembled from many parts. The architectural point is that dependencies shape attack surface, so you need deliberate controls around them. To use SCA effectively, you begin by treating dependency knowledge as a first-class architectural artifact rather than a developer-only detail. Architecture decisions often assume things about how input is processed, how authentication is handled, or how cryptography is implemented, and those assumptions may actually be fulfilled by third-party libraries. If you do not know which library performs a critical function, you cannot evaluate whether the function is trustworthy or whether it is maintained. Visibility matters because it lets you connect a design requirement to a specific component, which is a prerequisite for validation and remediation. It also helps you reason about where a dependency sits relative to trust boundaries, because a library used in a public-facing request handler has very different risk than a library used in a low-privilege internal utility. When dependencies are invisible, risk becomes vague and political because people argue based on feelings rather than evidence. When dependencies are visible, risk becomes an engineering problem with options. A closely related concept to SCA is a software bill of materials, SBOM, which is a structured record of the components included in a software product. You can think of an SBOM as the output that makes SCA durable, because it captures the dependency inventory in a form that can be shared, reviewed, and rechecked as the system evolves. The important beginner idea is that you cannot protect what you cannot name, and you cannot respond quickly to new vulnerability news if you cannot tell whether you use the affected component. An SBOM supports rapid answering of questions like whether a vulnerable library is present, which versions are in use, and which products or services include it. That speed matters during real incidents, where time pressure makes confusion expensive. It also matters for long-term hygiene, because it supports consistent updates and policy enforcement across teams. Even without going deep into formats, the architectural value is traceability between what is built and what is deployed. Static vulnerability counts can be misleading if you do not connect them to reachability and exposure, and this is where many teams drown in noise. SCA will often report many known vulnerabilities, but not all of them are equally relevant to your system. Some issues may exist in code paths you never use, while others may be directly triggered through your most exposed interfaces. An architect uses SCA results as inputs to prioritization, asking where the dependency sits, what data it touches, and whether the vulnerable behavior is reachable through realistic workflows. A vulnerability in a parsing library used at the boundary where untrusted input arrives deserves urgent attention because it may enable remote exploitation. A vulnerability in a test-only dependency or a library that is not deployed may still matter, but it should not distract from high-impact paths. The goal is not to ignore findings, but to prevent low-value noise from hiding the issues that threaten architectural trust. This is how you keep SCA effective rather than exhausting. The most meaningful SCA workflows also connect dependency risk to design mitigations that reduce blast radius even when vulnerabilities exist. You cannot assume every dependency will always be safe, so architecture should limit what a compromised component can do. That means enforcing least privilege for services that rely on many dependencies, reducing unnecessary access to sensitive data stores, and segmenting high-risk processing components away from critical control planes. If a vulnerable library exists in a component that has broad network access and high privileges, the risk is much higher than if that component is isolated and constrained. In this sense, SCA is not just a tool for patching. It is feedback for architecture quality. When your system is designed with containment in mind, dependency vulnerabilities are less likely to become catastrophic breaches. A beginner misunderstanding is thinking the only response to dependency risk is updating versions, when strong boundaries can reduce harm even while updates are planned. Good architecture turns dependency risk into manageable risk. Version management is one of the practical areas where SCA influences architecture decisions because uncontrolled version drift is a common cause of surprise. Different teams may pull different versions of the same library, and transitive dependencies can cause hidden upgrades that change runtime behavior. When versions drift, security behavior can drift too, such as changes in how tokens are validated or how inputs are parsed. SCA helps you see this drift and encourages standardization, where the organization defines approved versions and upgrade paths for critical components. Standardization is not about rigidity for its own sake. It is about reducing unknown variation so validation and testing remain reliable. If you know that a specific library version is used for cryptographic operations across services, you can validate behavior consistently. If every service uses its own version, you multiply the chance of subtle failures and multiply the work required to respond. From an architectural standpoint, managing versions is part of managing consistency, which is a core security quality. Licensing and provenance can feel unrelated to security at first, but they connect directly to supply chain trust and long-term maintainability. SCA often includes license identification because licensing constraints can affect whether you are allowed to ship or modify certain components, and last-minute surprises can lead to rushed replacements that introduce security gaps. Provenance refers to where a dependency comes from and whether its origin is trustworthy, which matters because attackers sometimes publish lookalike packages or compromise distribution channels. Even when a component is not malicious, an unmaintained dependency can become risky simply because it stops receiving fixes. For beginners, the security lesson is that supply chain trust includes social and operational factors, not just technical ones. A dependency maintained by an active community with clear release practices may be safer than a dependency maintained sporadically by a single person, even if both are functional. SCA brings these factors into view so you can make deliberate choices rather than accidental ones. Another place where SCA supports architecture is in building policy guardrails that prevent risky components from entering the system unnoticed. A policy might define what kinds of licenses are acceptable, what minimum maintenance criteria are required, or what vulnerability thresholds trigger review. The key is that policies must be actionable, meaning they lead to clear decisions such as blocking certain components, requiring exceptions with documented compensating controls, or mandating upgrades within a defined window. Policies also help reduce politics because they replace ad hoc arguments with shared rules that were agreed upon earlier. When someone wants to introduce a new dependency, the question becomes whether it meets the policy, not whether a reviewer personally likes it. For beginners, this is an important point because it shows how architecture governance can be proactive rather than reactive. A good policy system also supports learning, because people understand why certain choices are risky and how to choose safer alternatives. SCA provides the evidence needed to enforce policy consistently. Supply chain risk is not only about code libraries, because modern delivery often includes containers, build images, and infrastructure components that bring their own dependencies. SCA principles extend naturally to these layers because the architecture is shaped by what you deploy, not just what you compile. If your deployment includes a container image with many unused packages, you increase attack surface and increase the number of components that can become vulnerable later. If your build process pulls dependencies from multiple sources without clear trust boundaries, you increase the chance of substitution or tampering. Architectural decisions like minimizing images, reducing unnecessary packages, and standardizing build sources are therefore supply chain controls, not just optimization. The beginner takeaway is that dependency risk exists wherever software is assembled, including build and deployment layers. SCA is a mindset as much as a method. Know what you include, minimize what you do not need, and control the pathways by which components enter production. SCA is also most valuable when it is paired with a clear remediation strategy, because identification without action can create helplessness. Remediation often includes upgrades, but it can also include replacing a dependency, disabling a vulnerable feature, or isolating a component so the vulnerable behavior is unreachable. Sometimes you apply compensating controls like restricting network access or limiting privileges while a full fix is developed and tested. The architectural contribution is selecting mitigations that reduce real risk, not just that reduce a report count. For example, if a vulnerability exists in a library used only for a rarely used feature, you might temporarily disable that feature to remove exposure while planning a safe upgrade. If a vulnerability exists in a critical shared library, you might prioritize standardizing the upgrade across services to reduce drift and simplify testing. The point is to connect SCA findings to concrete decisions that change exposure and blast radius. This connection keeps the practice productive and prevents teams from becoming numb to repeated alerts. To prevent drowning in dependency alerts, it also helps to develop a habit of categorizing findings by the architectural property they threaten. Some findings primarily threaten confidentiality, such as vulnerabilities that could leak data through unsafe parsing or insecure transport behavior. Others threaten integrity, such as flaws that allow tampering or unauthorized changes. Others threaten availability, such as weaknesses that cause crashes or resource exhaustion under crafted input. Still others threaten trust and accountability, such as compromised dependencies that could alter logging or bypass checks. When you categorize in this way, you can connect findings to the system's critical workflows and decide what must be fixed immediately. You also become better at communicating risk because you can describe what could happen in plain terms rather than in vulnerability jargon. For beginners, this is especially important because it turns SCA results into understandable stories about system behavior. It also reinforces that the goal is protecting system properties, not achieving a perfect scorecard. A practical security architect is someone who can map technical findings to real outcomes. In the end, using SCA effectively is about turning the messy reality of modern software into something you can reason about, manage, and improve. You inventory what you ship, you understand how dependencies enter and evolve, and you use that visibility to control exposure and reduce blast radius. You treat vulnerability alerts as starting points that require context, reachability thinking, and prioritization aligned to trust boundaries and sensitive data flows. You use SBOM practices to make your dependency knowledge durable and shareable so response can be fast when new issues emerge. You build policies that prevent risky components from sneaking in unnoticed and that reduce politics by making decisions consistent. You design containment and least privilege so a vulnerable dependency is less likely to become a catastrophe, and you plan remediation so findings lead to real change rather than fatigue. When you can do these things, dependency risk stops being an invisible threat and becomes a normal, governed part of security architecture work.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.